Hello guys, so it is the part 4 of the video, and in the part 4 we are asked to calculate the surface area by summing the magnitude of cross product of vectors defining discrete parallelograms in part 3. So what does that actually mean? I will tell you. And then we have to compare that value against the traditional method by calculating the arc length and surface area. Like I said, like we will calculate 2 pi r the surface area and h 2 pi r h will look at the surface area of the helix. Then we'll compare that. So what does that this mean? Like cross product of vectors defining the discrete parallelograms. So let's go back to our uh, code. So this is our code which we've got over here. So the question wants us to say here, as you can see, there are several rectangular boxes or you can say parallelograms over here. So how are you going to calculate the area of parallelogram? The strategy over here to calculate the surface area, we're going to calculate the area of each parallelogram and then we're going to add of everything, all the parallelograms. So in this way, we're going to get the area of the entire surface of the helix. So over here, if you see closely, let me change the color. Let me change the color. Let me see. Let me change it to maybe something like black. Would it help? Let's see. No, it won't help. Black or let's say yellow or let's say green. And let's make the ellipse as mm, something subtle like yellow. Okay, let's see. Maybe it looks a bit better. Yeah, now I think you guys are able to see this. Yeah, you see there are two parallelograms over here. This one, another this one. Okay, so we need to calculate these. So this is the parallelogram. We need to calculate the area of the parallelogram. And area of the parallelogram formula is, let me show you. Let me show you by diagram. So this is our helix. I'm just taking a. Okay, this is our helix, and this is the cross sectional area. Is going like this. Okay, so if you take this area, look closely. It looks like this, something like this. You see? Okay, now what I'm going to do, we're going to calculate the area of these parallelograms and then we're going to add all of the parallelograms. Means total how many parallelograms are there? We're going to add all of the areas to get the area of surface area of this helix. So what's the strategy over here? How you going to calculate the area of this parallelogram? Even if you know that and to do that, you need to get the vectors over here. This vector and this vector. Okay. So to do that, the strategy is, see, this is our theta, means this is our t changing over this direction. And this is the theta is changing over this direction. Okay. If you able to find the delta theta, means the unit length of the time or t which changes in this direction, and the unit theta which changes in this direction, then what we're going to do, we're going to calculate. We have the surface function which has two parameters t and delta theta. We're going to calculate the Jacobian with respect to t and theta. So we're going to get the Jacobian with respect to this one and this one. Means how the points, like the point, some point is over here like x, y, and g. So we're going to, this is the surface. So s is equal to x, comma y, comma g. Okay. We're going to calculate the Jacobian with respect to t first, dt by dx by dt, ty by dt, tg by dt. Okay. Then we're going to multiply by delta t. Okay. Then we're going to know the this vector. What is this vector? Okay. Unit length of this vector. And similarly we're going to do with dou s by dou theta, how it changes in this direction, how it changes in, let me show you, how it changes, how the theta changes in, how the vector changes in this direction, which you can get by dx, how the x, y, and g changes with this direction with theta, dou y by dou theta, similarly dou g by dou theta. And to get the vector, we'll multiply with delta theta. Okay, once we get that, we got the both the vectors, we got both these two vectors, okay, this vector and this vector. Now what we're going to do, do the cross product to get this area of this parallelogram. Okay, then we're going to conduct the same thing with put the theta same with the same theta, but we'll change going to we'll put the same t with but we'll change the theta. And similarly with same t we're going to put the another theta. So we'll find the first area. First with same t we'll get all the theta. So this area we're going to cover. Similarly we're going to next t, t2. We're going to calculate all the thetas like this. So we're going to cover this one. Similarly, we're going to this part. Like this, we're going to add all of them to get the surface area. Okay, I think you understood. And the second thing, we're going to explain that after this. So first thing, we're going to do this. So let's get into the coding. So first, we need to get the Jacobian of the surface. So let's take some variable like surface area. Okay, surface area is equal to Jacobian of surface. As I have told earlier, the arguments which you have to show over here, if you don't give anything, it will going to take the Jacobian with respect to the first argument. But you need to, if you want to take both, Jacobian with respect to both the arguments, you can just put 0, means for the Python indexing, 0 means the first argument, comma 1 means the second argument. Now we're going to define a function. Let's call it surf area. Surf D area. Let's call it surf D area. Surf D area. It will take T and theta. And okay, so at each there are two Jacobians are there with respect to T and respect to theta. I need to unpack them. So let's do it like D surface D T comma D surface D theta, which is equal to our surface area with respect to T and theta. Okay, so we'll get that. Then it will going to return what we need to do. We got the ds dt. Okay, we need to multiply it with the delta t. Okay, delta t we have to calculate. Let's calculate over here. Delta t is nothing but the unit difference between the t's. So this is the first, second value of t is, means that the t values t's minus the first value of t's. T. Similarly, we're going to do with the thetas. Theta is equal to theta s thetas 1 minus theta 0. Okay, we got delta t and delta theta. Let's multiply them. delta t, comma ts t theta multiply delta theta. Okay, we're going to take the cross product of these two. So let's take cross product in CNP dot cross. I got the cross product. So once you get the cross product, you got the vector, and you need to take the what you call magnitude of the vector to get the perfect area. So it is the delta theta. Okay, delta theta. So to calculate the what you call the magnitude of this vector, you can call this GNP dot linear algebra dot hum. Okay, so got this now. To put several values of t's and thetas, we're going to vectorize this. So we can write this surf t area vec is equal to surf t area vec is equal to we'll call GNP dot vectorize. We'll put the values of we'll put the function which you want to vectorize. In our case is surface area, and the signature would be. So we have already done this previously. Here we are putting two scalars just like before, so there won't be anything inside. But and in return, what you are getting a scalar only, because area is a scalar. There is no direction. But over here, we have did you are getting a vector quantity. That's why we put 3. Now it's not required, so we'll just leave it blank. It's a scalar. We got the surface area. Now let's put surface d area. We'll put the values of e's, all the t's and thetas. Okay, you see here there is one problem. As you can see, we have calculated means the t's values are started from, where is the t values? Yeah, it started from 0 to 6 pi. Okay, so what happens over here? So it starts from for example, it starts from 0 to 6 pi. Okay, so what we're going to what and we'll have to calculate different 100 values are there in between. For example, let's take a small example. For example, it's start from 0 and ends at 5. Okay, then if there are 10 parts in between, or 5 parts, 1 2 3 4 5. One. So how many parts it became? How many points are there? How many points are there? 1 2 3 4 5 6 7. 3 3 6 7. Okay, so how many differences you get? 1 2 3 4 5 6. Okay, for 5 points you are getting 3 1. Okay, let me explain you properly. I got confused over here. So it starts with 1, right? Here, 1 2 3 4 5. Okay, so how many values you are getting? You're supposed to get 5 points, 5 values. 1 2 3 4 5. But in this case, you are getting 6 values. Okay, if you calculate the 5 one also. So you have to stop here only. Okay, stop here only. So that's why we're going to deduct, just you're not going to calculate the end value as per the Python indexing. Okay, so another example you can take like this. This is the circle. Okay, we're calculating 2 pi. Starts from 0 to 2 pi. That's pi by 2 then pi, 3 pi by 2, then again 2 pi. So the first thing will come like this one, this part, then second this part, third this part, fourth this part, and again 2 pi is there. So we're going to just do the normal take subtract from 2 pi to 0 and just do like that. So we're going to calculate this part again. So we're going to calculate this part two times. That's why we're going to take it till this point only. Okay, so we're going to neglect the last value. Okay, saying something. Okay, we're going to neglect the last value. So we're going to put like -1 and none, just for the broadcasting purpose. Then it also ends with -1 because we're going to neglect the last value, and none. Okay, now it should run. The surface area. Okay, it should be back. I did a mistake. Okay, it should be back now. Okay, let's run it again. Maybe something happened. Session crashed, that's why it's not running. Let's run everything again. We got our helix. Okay, now we're going to get all the values. Okay, it's saying what is this? Surface area vector, chain field vectorize, surface area signature. Okay, we're putting everything. See what is the error over here. Okay, surf T area back. What are the T's? T's. We're going to put the T's and thetas. T's. Let's put the last value to the broadcasting, comma, thetas. We'll do the broadcasting, then create the last value. Okay. It's saying cross missing one required positional output B. I don't know what they are saying. Maybe I missed some. Okay, let me see what's the error over here. Delta T, Ts minus Ts, delta theta, thetas minus theta, so on, theta 0. Surface area checks Jacobian surface 0 to 1. 0, 1 means we're going to take derivative with respect to both the arguments. And then TSTT, save that. TS T theta, surface area, surface T area, then JNP norm, JNP dot cross product of DSTT into delta theta, delta T, DST theta into delta theta, that's right. D surface area vector, I will read the vectorization of this thing. JNP dot vectorize equal to surface D area, comma signature, giving two scalars, getting one scalar. It's right. Till this point, everything is right. Let's put one value of T and theta and C. 0 dot and pi by 4 or something like that. Okay, cross missing one argument. Maybe some issue with this cross jnp dot cross. Not getting it. What's the error over here? Okay, maybe some error is over here. jnp dot lin algebra dot is equal to take jnp dot cross product of ts tp multiplied by delta t comma ts t theta multiplied by t theta delta theta. Okay. Okay. So I made some mistake over there maybe. Anyways, now it's running fine. So let's put the values of t's and thetas. T's, I just said it is the last value, and thetas, let's put the last value, and again we have to do the broadcasting. None, same thing as before. Got all the values, just need to add them. These are the values of all the what you call all the parallelograms along the helix. Okay, so let's now add them. Okay, we got this area. Okay, let's save it as helix surface area. Okay. Area. Okay. Now the second method. Okay, this is the area I got. Now we have to compare by calculating the area by the traditional method. So what is the traditional method over here? Let me explain you. Okay, so we got the helix like this. Okay. The helix is nothing but so you can think like this. Think this as a cylinder which has been coiled. So just take an example of just a normal cylinder. And how to calculate this area of the cylinder? If the length is L, or you can say H, then the radius is R. So the surface area will be 2 pi R into H. Okay, the length into the surface, means the what you call the perimeter of the circle or something. Okay. So over here also you can do the same thing. Like you can going to take the perimeter of this ellipse, then multiply the length with the length. But we don't have both the things. But we can calculate that. We have the helix function, which is the which we have taken. So we're going to get how we're going to get the length from this helix function. So the helix function goes like this. Starts from here, goes like this, and it moves along the t. So what we're going to do, we're going to take the Jacobian of the helix function with respect to t, and then we're going to multiply with delta t. So we're going to get the length, and to get the surface area, we have the surface function. We're going to take Jacobian with respect to theta and multiply with d theta. Okay, similarly as we did now, and just multiply both of them. Okay, so it's simple mathematically. So let's do it and see how much you are getting. So helix length is equal to, we're going to take Jacobian, right? Jax dot Jacobian with respect to the helix, and we're going to take the no, we're going to take the derivative with respect to the first argument. So if you want to give a zero, it's good. Otherwise, it's not required as well because we're going to take the derivative with respect to the first argument by default. Now let's make a function out of it. Helix, let's say as helix t length. It is going to take t. Theta is not required. So only one argument it is going to take, and it is going to return what it is going to return. Like we're going to calculate. Okay, that's it is going to calculate the helix length at t. Okay, you're going to get that into, you're going to multiply with delta t. Okay, we got this. Then we're going to take the, what do you call, take the magnitude of this vector. Okay, so it will be jnp dot alg len alg dot no. We got this. Now we're going to vectorize this. Helix t length vec is equal to jnp dot vectorize. Which function we want to factorize? Which is helix t length, comma. What is the signature for this? Not signature is, we are giving only one scalar and getting only one scalar out. So simple, simple. Okay. Now what we're going to do? We're going to we got these values, we vectorized. We're going to put the t values, different t values for each and every t, how it changes, and we're going to add the everything. Okay. So jnp dot sum helix length vec. We're going to put all the t values only, remove the end value. We're going to get the, okay. I forgot something over here. This is my mistake. I have to put t as the helix function. You have to put r and ng as well. Pass them because they are the parameters of this function. Argument of the function. I haven't passed them. That's why it's giving error. Now it should give. It's 76 we are getting. Okay, let's save it as len of len helix or something like that. Now we will calculate the surface. So surface, or you can say ellipse area, ellipse perimeter, ellipse perimeter is equal to, we're going to take derivative, right? Jax dot Jacobian of surface function we're going to take, and now here we're going to take derivative of surface function with respect to theta, because we just need not theta, it's only theta. We just need how this changes in this direction. Okay, and this is the theta. In theta direction, how it changes. And we're going to multiply with d theta. So we got this. What happened? Okay, we have to write 0 or 1. We can't write theta. And surface function has two arguments, which is t and theta. Over here you can see t and theta. This is 0, this is 1. So I'm putting 1. Now let's factorize this. Means gonna make a function out of this. Ellipse t perimeter, and we're going to pass in theta. Now what we're going to do is return. What we're going to return? We're going to return ellipse perimeter at particular theta multiplied by delta theta, and we're going to take the what you call GNP dot lineals dot GNP dot lineals dot space. No, okay. So we'll take the magnitude of this thing, and now we need to factorize that. So ellipse t perimeter vec is equal to GNP dot factorize. We'll pass this function. Which function you need to factorize? Ellipse t perimeter, and the signature is again the same because we're only giving a scalar and getting a scalar over here. Okay, now pass this all the values of thetas. So ellipse d perimeter vec, we're going to pass the thetas except the last value. Okay, what's the error over here? The d perimeter rejection, j to factorize. Okay, we need to, okay, see, the ellipse perimeter means the ellipse function, the surface function. See, we've taken the surface function, right? Jacobian surface function. So it has two parameters. We have to pass both of them over here. I just skipped it, that's why I got error. I have to pass both of them. Otherwise, just need to put 0 as well. Okay, now it will run definitely. Okay, we got this value. Now we're going to submit JNP dot summation of this. This is the ellipse peri. Ellipse peri, let's say like this only. Okay, so uh, surface area helix helix 2 we can say, which is equal to ellipse peri multiplied by helix length. Okay, so let's print the surface area 2. We got 372. Let's print both of them together to compare them. I think I saved it inside, right? Not saved. Oh, this thing is not showing. Okay, so this one I calculated first using the what you call using the vector method. Okay, and this is slightly bigger than this, around 0.05 no, 0.05 you can say meter, 0.05 meter square. It's very no uh, minute difference is there, and the difference is just because if you see you're calculating is in terms of a cylinder. If you're considering this is a straight cylinder, I'll calculate that. But when you bend it, so you'll see there were some bends in some of the areas, and due to the bends and bends of the at these points, the surface is stretched a bit. It gets stretched a bit, and that's why you can see the area is bit higher compared to this. Okay, so with this we have completed four parts of our video and homework, and so that's it, guys. Thank you. Thank you for watching.